So welcome to Advanced Mobile Communication course, my dear students. So today we are going to observe some mathematical proof related to the frequency reuse ratio. So in last class we have started the concept of hexagonal cell geometry. And we have seen some basic equations related with cell geometry. Now, I have mentioned that we are going to derive derive those formulas in our upcoming class. So today we are going to do some mathematical calculation and mathematical derivation of a formula, mathematical formula like this reuse distance, frequency reuse distance D is equal to √3n into R. We have discussed about this formula in our last class, but today we are going to derive this equation. Okay, and from this equation, we are going to determine the relation between the frequency reuse ratio Q, frequency reuse ratio, which is small q, it is denoted by capital D by capital R. Okay, so from this equation, from the value of D, we are going to determine the value of small q, which is the reuse ratio. Now, if you can remember about the hexagonal cell geometry, so just give attention to this particular figure here. So in this figure, we can see, okay, I'm going to go slow so that you understand all the relation between these equations. So just observe this figure here. So we are going to focus in this figure. Now in this figure, what you can see here, there are different numbers of hexagonal cells. Okay, so these are cells. Each of these are cells. Okay, so the shape of these cells are hexagonal. Okay, now this point is known as the cell center. This point is known as the cell center, and the distance between two adjacent cell center, between two neighboring cell center. This is one cell center, this is another cell center. And this distance is denoted by small d. This distance is denoted by small d, okay? The distance between these two neighboring cell centers. So this is small d, okay? Okay, so this is known as small d, and this small d, if we apply simple mathematical geometric formulas, then we can determine this small d is equal to 2r cos 30 degree. Okay, how? I will show you how. So what is this capital R? Now R is the cell radius. If you can remember, R is the cell radius. So say for example, this is one cell. This is another cell. This is cell center. This is another cell center. So this distance is denoted by small d. Now, this is small d. Now, what is cell radius? This distance or this value is denoted by cell radius r, capital R. Even this value or this value is same. Okay, it is also known as cell radius R. Okay, this should be equal for a hexagonal shape. So if I talk about the cell radius, then this point, and this all are same, which is R. And this, all these are denoted by cell radius R. Okay, so this should be same. So if you apply the simple mathematical formula, then the value of D will be, we can get this as 2R cos 30 degree. This is very easy. So I will try, if I get time, then I will try to show you in the last part of our lecture. Okay, but for the time being, just consider this D is equal to 2R cos 30. You have to just apply this formula. You know that if this is 90 degree, say for example, one triangle like this, this is 60 degree, this is 30 degree, and this is 90 degree, right? So we can write like this. If I want to write like this, that cos 30 degree. Okay, cos 30 degree, then what should be the value? Say for example, this is A, B, C. Then what should we write according to our mathematical formula? AB divided by BC, right? So we will just implement this formula and we will get this thing. So I will, if I get time, we will do this in the last part of our class. So for the time being, just consider D, small d is equal to 2R cos 30 degree. Okay, then let's continue our derivation. So all these are cells. Now, say for example, this is one cell, this is one cluster. Okay, say for example, this is one cluster. So in each cluster, we are having 7 number of cells. Now, this whole cluster or this whole bunch of frequencies or set of frequencies are going to be repeated in the neighboring area. Okay, so say for example, this is another center of the cluster, and this is another cluster like this. Okay, so this is F1, this is 1, 2, 3, 4, 5, 6, 7. This is one cluster. So combining these 7 cells, we are having this one cluster, and combining these 7, like 1, 2, 3, 4, 5, 6, 7, we are having another cluster. Okay, now what we are going to derive? We are going to derive the distance between the 2 center cells of these 2 clusters. Okay, so the first cluster, say for example, this first cluster, this is the center cell. This is the center point of this center cell. Okay, this is the center. And this cluster number 2, this is the center cell. And this is the center point. Now, what is happening here? we are reusing, say for example, here we are using the F1 frequency set, and in this cell we are reusing the F1 frequency set. So we have to determine the value of the distance, okay, which we should maintain while reusing these frequencies. Okay, so in short, let's say this cell is using frequency F1, this star mark, okay, star mark, here is one star marked here. So this cell is using frequency F1, and this another star marked cell, this is also using the frequency F1. Now we have to determine this distance, okay, capital D. So this distance is known as frequency reuse distance, capital D. Okay, now we have to determine the value of capital D. Okay, the whole calculation we are doing for determining the value of capital D. Okay, so now let's consider this is the first cell. This is the center point. Now in this center point we have two coordinate axes. So this is our x-axis, and on the x-axis, if we take a perpendicular axis, another axis, which is known as j-axis. Okay, so we are having one x-axis, one j-axis. Now, when we are taking 60-degree angle in anti-clockwise direction, we are getting another axis which is known as I-axis. So in our previous class, we have discussed that the angle between j-axis and I-axis should be 60 degree. So this is 60 degrees. This is 60 degree. If this is 60 degree, then the angle difference between x and I should be 30 degree, right? So this should be 30 degrees. So this point is clear, and these j-axis, I-axis, x-axis are clear. Okay, okay. Now this is our center cell, or this is our first cell. So you have to go to say for example, we are taking one example. We are taking a cluster size with n is equal to 7. Now n is equal to 7 means in one cluster we are having 7 number of cells. Now for n is equal to 7, we have considered the value of I is equal to 2 and the value of j is equal to 1. So if we put the value of I is equal to 2 and j is equal to 1, we are getting the value of n is equal to 7. Okay, okay. Now for this 7 number of cells, now if we are considering this cell and we have to go to this j direction, sorry, I direction. We have to go through this I direction. So we are going through this I direction. How many unit? 2 unit, because the value of I is equal to 2. So we have to go 2 unit through this I direction. So I will go like this. I is equal to 1. I will get this point. Then I is equal to 2. I will get this point. Then on this point, from this point, I have to go through j direction. And how many unit I will go? I will go 1 unit, because the value of j is equal to 1. So I will go 1 unit through j direction. Now j is on this direction. Okay. So if I go onto the j direction, then I will go 1 unit through this j direction and I will get this point. Okay, so Let's repeat. Let's repeat. I am starting from this cell. I'm going through the I direction. This is my I direction, and I'm going to 2 unit. 2 unit means 1 unit means the small d is my 1 unit. Okay. So from this cell center to this cell center, 1 unit. From this cell center to this cell center, another unit. So this is my I equal to 2. Then another small d distance from this point to through the j direction. So I'm going to, so this is how I'm reaching to this point. Now it is the cell center of that cell where I'm going to reuse the frequency f1. Okay, so this is how I can start my journey from this point and end my journey to this point. Okay, if I use these values of I and j. Okay, now so you have got this point how I am traveling from this point to this point. Now let's consider this triangle here. Okay, there is one triangle which is marked by this yellow line. Okay, so let's consider this. Let's consider this triangle. Now from this triangle, I'm going to calculate the distance, capital D. Okay, this is my straightforward distance from this point to this point. Now I have to calculate this using the simple mathematical formula. So I'm taking this triangle out here. So this is my same triangle. This portion is just taken out here. So let's see, this is the capital D. Okay, this is capital D. This is capital D. This is capital D. Now what is this? So this is denoted by small b. This is denoted by small b, and this is denoted by small c, and this capital D is denoted by small a. Now the angle between the A and C is denoted by capital B. The angle between the C and B, small b, is denoted by capital A. The angle between the small a and small b, this is denoted by capital C. Okay. Okay. So we have just denoted different points for this triangle. Now, if you apply this cosine rule to this triangle, then you know that a square is equal to b square plus c square minus 2bc cos a. Okay. So this is the cosine formula for this triangle. So a square is equal to b square plus c square minus 2bc cos a. Now, what is a square? A square is actually our capital D square, right? This a is actually capital D. So we can write capital D square. Now, b square plus c square minus 2bc cos a. What is b square? B square means, so here we are putting these values. So now b square mean this value. B means this value. So this distance is denoted by small b. This is denoted by small b. Now what is small b? See, we are deriving one general formula. Okay. So here what we are doing, this small b is actually, I have said that from this cell center to this cell center, the distance is denoted by small d. Now here we are going one small d, 1d, then 2d. So this is actually, this small b is actually 2d. We can say this is 2d. Now what is 2? 2 is the value of I. Okay. So as we are deriving the general formula, so we can write, instead of 2, we can write I into d. Okay, I into d we can write. So b is actually I into d. So instead of b square, we are writing I into d square. Similarly, this value, which is denoted by small c, is actually this value. So what is this? This is also the difference between two cell centers. So this is also d, small d. Now here what we were doing, that we were just going through the j direction. As our j was equal to 1, so we have traveled 1d distance. If the value of j was 2, then we needed to go j is equal to 1, then j is equal to 2. J is equal to 2. So we could reach there if j was equal to 2. But here j is equal to 1, so we have reached to this point. So instead of writing d into 1, we can write d into j. So actually this angle, this value, which is denoted by small c, this is actually c is equal to d into j. So instead of c square, we can write j into d square. I hope you are getting my points. Now minus 2, instead of b, we are writing I into d. Instead of c, we are writing j into d. Now cos A is the angle between this value, this small b and this small c. Okay, this is this angle. So now here this angle is, we have to derive this angle. So see, let's just see that this is our I axis and this is our j axis. Now we know that between I and j axis, we have to maintain 60-degree angle difference. So if this angle is 60 degree, then obviously this angle is 120 degree, right? 180 degree minus 60 degree is equal to 120 degree. So the angle between B and C should be equal to 120 degrees. So we are writing cos 120 degree. Now the value of cos 120 degree is equal to minus half. So we are going to use this value later on. Now, okay, now let's calculate. So capital D square is equal to I square D square plus J square D square minus 2 IJ D square cos 120 degree. Now the value of cos 120 degree is minus half. So we are taking D square common. So here is I square plus J square minus 2 IJ into minus half. Now this minus will be plus. And these 2 and 2 will be neutralized. So we are having I square plus IJ plus J square. Now, if we observe, this equation actually represents the value of n. See, n is equal to I square plus IJ plus J square. So this is actually n. So we are substituting this equation with capital N. And in case of d square, small d square, now here you can see that d is equal to, small d is equal to 2r cos 30. And in the beginning, I have said this formula that small d is equal to 2r cos 30. Now the value of cos 30 is equal to root 3 by 2. So this 2 and 2 is cancelled. So we are having root 3r. Okay, root 3r. Now, instead of d square, we are using this formula. So if you square this, so what will you get? 3r square. So we are using 3r square. Now, we are getting capital D square is equal to 3r square n. So if you do root over in both direction or both side, then you will get D is equal to root 3n r. Okay, so this is our capital D. Now we know that the reuse ratio can be referred as capital D divided by capital R. This is our reuse distance. This is our cell radius. So if you use the value of capital D, which is 3√3n into R. Now this R is cancelled, so we have √3n. Okay, so this is the value of the reuse ratio. Okay, okay. So this is how we are actually deriving this formula here. So in your exam, you can get any question to derive this formula. Okay, that in the question I can give that derive Q is equal to √3n. Okay, or I can say that derive the formula for the frequency reuse ratio, which is the small q. Okay. Now, okay. So now let's go to the next slide. Now the reuse distance and co-channel interference. What is co-channel interference? Okay, what is co-channel interference? What is reuse distance? We have derived the value of reuse distance, which is actually the capital D. Okay, so capital D is derived as √3n into R. Okay, this R is the cell radius. Now, capital N is the reuse pattern, the cluster size or the number of cells per cluster. Now, reuse factor, we have seen these points. Now, what is the co-channel interference? So the co-channel interference means, say for example, I'm using F1 set of frequency in this cell and I'm reusing this F1 frequency set in this cell as well. Now there can be some interference between these two cells. Okay, there can be interference between these two cells. So that interference is known as co-channel interference. When two signals having the same frequency, say for example, in this cell, from this cell, one base station is transmitting some signal within F1 frequency, and from this base station, this transmitter is also transmitting some signal with F1 frequency. So that those two signals can create interference for each other. For example, this signal from this cell can cause interference to this signal, and the signal from this cell can cause interference for this cell. So that interference is actually known as co-channel interference. Okay, there is another term called adjacent interference, adjacent cell interference. Now, what is adjacent interference? Say for example, say for example, this two cell, one cell is using F1, one cell is using F2. So the signal which is using F2 and the signal which is using F1, both of these signals can create interference for each other. Okay, but as they are having different frequency sets, so that interference, when the signals are using different frequency, that interference is known as adjacent interference. Okay, so this is actually the difference between co-channel interference and adjacent interference. Okay, okay, so the next point, let's go to the next point. Now let's understand the co-channel interference for this cluster. Say for example, this is one cell, this is the center point of this cell, and here is one cluster. Okay, here is one cluster, and there are another clusters. So in these clusters, this cell is using this frequency. Say for example, this is using F1, and these orange colored cells are also using F1. So they will create, so these cells will create co-channel interference for this center cell. Okay, okay. Now just observe that these these cells are known as first tier co-channel base station. Now, when we are, we can assume like this, in this circular area can be termed as first tier, and these bigger circular area, this can be termed as second tier co-channel base stations. Now, in the practical case, the impact of first tier co-channel base stations are significant. Okay, so they can be considered, but the impact of second tier co-channel base stations are very negligible. So we can neglect these second tier co-channel base stations. Say, for example, there are also another clusters and they are also using F1. There are also cells which are using F1, but we are not counting them, because that for this cell, from this cell to this cell, the distance is very high, and this cell cannot create any interference for this cell. Okay, if it creates some interference, that will be very low, and that can be neglected. So we are going to neglect this second tier co-channel interference. We will only consider on the first tier co-channel interference. So in my first tier, I am having these cells. So I have to consider the interference occurring from these cells for this serving station. Okay, say for example, this is my serving base stations. So for this serving base station, these cells are creating interference. So I have to calculate the interference I'm getting from these cells. Okay. Okay. Now, say for example, just observe this figure. This is my serving base station. This is my cell center, and this is my mobile station. My mobile station can move to any place. So it can be on the center point. It can be on the outer portion. It can be on this portion. It can be on any of these point in between this cell. Okay. Now the distance from this cell center to this mobile station can be considered as D1. The distance from this cell center to this mobile station can be this point to this point can be D2, D3, and up to D6. Okay, so the distance from the interfering cell, center point of the interfering cell and the mobile station is denoted by D1, 2, 3, 4 up to D6. Okay. Now let's calculate this signal to interference ratio or co-channel interference. Okay, co-channel interference, or which can be calculated by signal to interference ratio. Okay, so we know that signal to interference ratio can be written as signal power divided by interference power. Okay, now the co-channel interference ratio is given by this equation. So this is signal divided by interference. Now signal is denoted by S and interference is denoted by IK. Now the value of K. Now there are not, say for example, this is my serving station. So this is serving, or this is transmitting a signal whose power is S. Okay, so my serving base station is 1, but my interference creating cells are of multiple numbers. So they are like 6 in number, right? 1, 2, 3, 4, 5, 6. So there are 6 numbers of interfering cells. So say for example, if this cell is creating interference I1, this cell is creating interference I2, I3, I4, I5, I6. So I have to consider all these. I have to take I1 plus I2 plus I3 ... plus I6. So I have to take all these in account. So I am taking like this, I am taking ik. Now the value of k should be equal to, and there should be one summation symbol. So the value of k should be equal to 1 to 6, or we have taken one general formula. So k is equal to 1 to m. Okay, now m, here m is equal to 6. Okay, m is equal to 6. So the interference can be written as summation k is equal to 1 to m I k. The value of k will be changed from 1 to 6. So I1 plus I2 plus I3 plus dot 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 plus I6. So this is how I am just adding all 6 interferences from these 6 interfering cells. Okay. So I is the co-channel interference and M is the maximum number of co-channel interfering cells. Okay. Now, if we put M is equal to 6, then S by I is given by co-channel interference ratio is equal to S by. Now, this I is written as dk divided by R. Okay, dk divided by R. What is d? What is dk? dk is the distance between this center point and the mobile station. Okay, so this distance is actually denoted by dk. R is the cell radius, and gamma. What is gamma? This is actually one formula for calculating interference. So interference is actually related with the distance. If the distance is larger, the interference is less. If the distance is lower, the interference is higher. Okay, so this interference is actually related with D, and this gamma is actually the propagation path loss slope. So the value of gamma can be considered from 2 to 5. It can be from 2 to 5. Okay. Okay, so this is my propagation path loss. Now, if we assume dk is the same for 6 interfering cells, say for example, if my mobile station is on the center point of my cell, then all the distance from this center point to this point, from this center point to this point, so all distance will be same in that case, right? So say for example, if my mobile station is on the center point, then all the distance will be equal to d. So all dk will be equal to d. So instead of this, I can write 6 into d by r. Okay, so I am writing 6 into capital D by R to the power minus gamma. And I am taking transmitted signal S is equal to 1 here. For simplification, I am taking S is equal to 1 here. Okay. Now, how the equation looks here? So S divided by I is equal to, sorry, here, S divided by I is equal to 1 divided by 6. D by R is replaced by small q. We know the frequency reuse ratio. Q is equal to capital D by capital R. So instead of capital D by capital R, we are writing frequency reuse ratio. So small q. Now the equation is like this: S by I is equal to, I am taking this point like it is like 1 by 6 q to the power minus gamma. So I am taking this like this: q to the power gamma divided by 6, right? So I am writing like this: q to the power gamma divided by 6. So if I take the value of q, then this equation will look like this: 6 into S by I to the power 1 over gamma. Okay. So my co-channel interference will look like this. And if I want to determine the frequency reuse ratio, the q, small q, in case of with the relation of co-channel interference, then the value of q can be written like this. So you have to remember this formula and you have to remember this formula as well. Okay. Now, the worst case of co-channel interference. So this is the best case of co-channel interference. Okay, when the co-channel interference is minimal. Now the worst case of co-channel interference. Now, what is the worst worst case of co-channel interference? So when my mobile station is at the edge of the cell. So this is the worst case. Okay. So when my cell is when my mobile station or mobile user is at the edge of the cell. So just pay attention that here the distance between this mobile station and this point. Now, see, the distance between this center and this point is r. So this is actually capital R. So the distance from this point to this point is capital D. Okay. So the distance between these two cell center is capital D. We know. Okay. This is capital D. Now, when my mobile station is at this point, so the distance is capital D plus R, capital D plus R. So this is actually D plus R. So this point also D plus R. This distance also D plus R. This distance can be written like D. This distance can be written like D. And this distance can be written like D minus R. As this point is moving toward this cell, so this distance is reduced, right? So this distance can be written like D minus R. This distance is also reduced. So this can be written like D minus R. So we have total 6 cells or total 6 distances. So 2 distance is D plus R, 2 distance is D, and 2 distance is D minus R. Okay. So when we are calculating the value of co-channel interference S by I, we are writing like the value of, say for example, this. So instead of dk by r, you are writing d minus r by r, d by r, d plus r divided by r. So that divided by r is taken here. Okay. R to the power minus gamma. This is actually taken here. So we have 2d minus r to the power minus gamma, 2d to the power minus gamma, 2d plus r to the power minus gamma. So now if you take the r as common, you will get like this, as we know that d by r is denoted by q, small q. Okay, so you are actually dividing by r. You are actually dividing by r. Okay, the denominator and the numerator, you are dividing by r, capital R. So you are getting this equation. So we will get 1 here, and here we can get 2 into q minus 1 to the power minus gamma, 2q to the power minus gamma, 2q plus 1 to the power minus gamma. Okay, so this is our worst case for co-channel interference. Okay, now if we assume the value of q is equal to 4.6, okay, the value is 4.6, then we can get the value of co-channel interference SI as 54.3. If you put q is equal to 4.6 in this equation, and you can take the value of gamma from 2 to 5, then you can get the co-channel interference like 54.3 or 17.3 dB, which is lower than 18 dB. Okay, so it should be above 18 dB. Okay, it should be above 18 dB. If the co-channel interference is above 18 dB, then it is some acceptable point. And if it is lower than 18 dB, like for this case, so this is the value for worst case. Okay, worst case for our co-channel interference. Okay, so this is the end of today's lecture. Now,